So here is kind of the L'Hopital's rule light, meaning not saying like all the things, but saying enough so that we understand what we need to do. So here is L'Hopital's rule in a nutshell. Also, just a personal plea. Please don't say Le Hospital. Please say L'Hopital in the French, like it's meant to be said. That's an accent circumflex. Anyway, not that important. If you say Le Hospital, I won't even hear you. So, so L'Hopital's rule says the following. If f of x and g of x are differentiable, really like at the point or at the point we're interested in, but really just like differentiable, then we have the following. If the limit as x approaches a of f of x over g of x is equal to either 0 over 0 or sum infinity over infinity. And the reason I say sum infinity over infinity is because it doesn't really matter if they're the same or not. Meaning this could be infinity and this could be minus infinity. This could be minus infinity, this could be infinity. They could both be positive, they could both be negative. It doesn't matter as long as they're both some sort of infinity. So something like a plus or minus, plus or minus. So there's 4 different possibilities here, right? Positive, 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 negative, negative, positive, negative, negative. You've got some sort of indeterminate infinity over infinity. Then we get to say the following. The limit as x approaches a of f of x over g of x is equal to the limit x approaches a of f prime of x over g prime of x. So the limit of the quotient is equal to the limit of the quotient of the derivatives. And that's with the caveat, of course, that provided this exists. Okay. And so we're not going to prove this. Usually we try and prove things and just justify them in some sort of way. I am going to offer a bit of an explanation that I think is actually, I didn't come up with this, but I think it's rather clever. So why would this be true? Well, yeah, I'm going to actually draw up things. So let's say we have a couple cars and the driving, as cars are wont to do. So let's say we've got car, come on, bends. I've got car, so I've got car A, and I can't draw cars nearly as well as the person who's drawn this. Going that way, got a big trunk, and that's car A. And then down here we've got car B. Another car. Wow, my cars are really not good. That's more of a truck. All right, my cars have gotten noticeably worse since last time I tried to draw them. This is car B. And they're both going that way. And here's what I want to say about these things. Well, a couple things. First of all, let's say that A of t is the distance for car A. As a function of time. So A of t is the distance car A has traveled at time t. And let's call it A prime of t, right? The derivative of distance is velocity. So A prime of t equals the velocity of car A at time t. Same deal for B, right? B of t equals distance for car B. B prime of t equals the velocity for car B. Now check this out. This is kind of the interesting part, I think. So suppose both cars travel for an infinite amount of time. So suppose both cars travel, which I know is not realistic, but come on, that's math. It's never real. Well, that's something realistic. Travel for an infinite amount of time. And also, or I should say but car A travels twice as far as car B when you get to the end of infinity, which isn't really a thing, but okay. So what does that mean? Well, using limit notation, here's what that means. So this is where everybody should like really be paying attention. If after an infinite amount of time traveling, car A travels twice as far as car B, it really means that we're saying the limit as t goes to infinity of the distance car A traveled divided by the distance car B traveled. Well, if after an infinite amount of travel, car A has traveled twice as far as car B, then this limit should be 2 because car A has traveled twice as far. So the ratio of their distances traveled, this one should be twice as much as that one. Okay. But now here's the thing. What does that mean about their velocities? Well, if car A traveled twice as far, it had to have been going twice as fast if they've been traveling for the same amount of time. So we could also say the limit as t goes to infinity of the velocities in ratio should also be 2, right? Car A should have been traveling twice as fast as car B if they're traveling for the same amount of time. Not that this is a justification, but I feel like this is somewhat of an explanation as to why this should actually be the thing that's true, right? If something travels twice as far as something else for the same amount of time, in the same amount of time, it should have been going twice as fast. So hopefully that makes some amount of sense. I think it's not a terrible example. I kind of like it. In any event, let's actually talk about how to use this. And I'm going to start off with some examples we know. We know some limits already. In fact, here are 3 limits we already know the answers to. Oh, Jesus, oh my gosh. Sorry. So we know that the limit as x goes to 0 of sine x over x. What's that limit equal to? Anybody? 1, right, exactly. We know that's equal to 1. We also know that the limit as x goes to 0 of sine of 5x over 2. I don't want to do that, actually. I'm going to encourage some bad habits there. We know the limit as x goes to infinity of 3x squared plus 4x plus 2 over 7x squared plus 6x minus 9. I'm surprised no one's written the answer yet. What's this limit equal to? Exactly. And this last one is probably a little bit harder. The limit as x approaches 3 of x squared minus 9 over x minus 3. If you factor and cancel, you get x minus 3 times x plus 3 over x minus 3. The x minus 3's cancel, and you get x plus 3. You plug in 3, you get 6. All of these limits we could do without L'Hopital's rule, and I will point out later on that, and now, that sometimes it is actually advantageous to not use L'Hopital's rule. There are times when you can use L'Hopital's rule that you shouldn't, because it's just awful. But in these 3 cases, although we could certainly do them with methods we already have, L'Hopital's rule also provides the correct answer. If I use L'Hopital's rule here, and I typically, if I'm using L'Hopital's rule, I think it's a good idea to write an L'H above the equal sign that's between the steps of using L'Hopital's rule, just so that the person grading my work knows I'm using L'Hopital's rule. So I'm taking the derivative of the top and the derivative of the bottom. The derivative of sine of x is cosine of x. The derivative of x is 1. And now when I plug in 0, I get cosine of 0, which is 1 over 1, which is 1. I should back up a tiny bit and say, I was able to use L'Hopital's rule here because this limit met the conditions. It's a limit of the form 0 over 0. Sine of 0 is 0, and 0 is 0. So we can only use the L'Hopital's rule if we have a 0 over 0 or an infinity over infinity type of limit. Any other thing, you either can't or you have to do some work before you can. Here we couldn't use L'Hopital's rule. It's no longer a 0 over 0 or infinity over infinity. It's a 1 over 1, that's just 1. In this example, it is infinity over infinity. The top is definitely going to infinity. The bottom is also going to infinity. So I'm going to use L'Hopital's rule. A couple things about L'Hopital's rule. One, it's only for limits. I've definitely seen people try to use L'Hopital's rule when they're taking a derivative. L'Hopital's rule, right? L'Hopital starts with an L, kind of, and limits start with L. You should be like, oh, L'Hopital, that only goes with limits. So I'm going to take the limit, and it's a limit every step of the way until you actually get to your answer. So the derivative of the top is 6x plus 4. The derivative of the bottom is 14x plus 6. And I mean, you could just say it's 6 over 14, which is 3 over 7. Or you could use L'Hopital's rule one more time, because this is also an infinity over infinity. Right? The top is going to 6 times infinity plus 4. The bottom is going to 14 times infinity plus 6. So if I use L'Hopital's rule one more time, still have a limit, right? Every time I'm using L'Hopital's rule, I still should be writing the limit before anything else. The derivative of 6x plus 4 is 6. The derivative of 14x plus 6 is 14. And the limit of a constant is just the constant. So that's going to equal 6 over 14, which reduces to 3 over 7. I'm not saying you should use L'Hopital's rule for this problem. I'm just saying that L'Hopital's rule shows us that this limit is what we think it should be. Same deal here. We think this is supposed to be 6. Let's use L'Hopital's rule. So I'm going to get the limit as x approaches 3. The derivative of x squared is, I should say, the derivative of x squared minus 9 is 2x minus 0. The derivative of x minus 3 is 1. And I should have really said, this is a 0 over 0. And now when you use L'Hopital's rule, I have a not 0 over not 0. Plug in 3, 2 times 3 over 1 is 6. So yes, L'Hopital's rule definitely works for limits that we don't know. Or sorry, that we do know already. But it also works for some things that we haven't been able to deal with before. And one example that I want to start with, actually, not start with, but reference is, so we're not going to do this question yet. Maybe we will. Yeah. Yeah, let's see. Yeah. So we're going to take a quick step aside and do a graphing problem. So let's graph something relatively easy. Let's graph relatively easy. No, we're not going to graph a thing. We're going to just refer back to a graph that we did before. So we graphed f of x equal to x to the 4th times e to the negative x. We did this 1 or 2 classes ago, and it ended up being kind of neat. There were inflection points, there were relative extrema. It ended up looking somewhat like, let's see, I have to remember what happens here. It does that. I don't remember where my critical values are, if they're positive places or negative places. Oh, they're at positive places. So I'm pretty sure my critical values are at 2, 4, and 6. That is, I know I have a relative maximum of 4, and I have inflection points at 2 and at 6. I have an X-intercept at 0. And when we graph this, it looked like this. And I said specifically, we knew that we had a horizontal asymptote over here to the right because of how the first and the second derivative looked. That was not entirely untrue, but there was other ways to do it. I'll remind you that our first derivative sign chart looked like this. Let's see, there was a 0 and a 4 as critical values, and it was negative, positive, negative. So it was decreasing, increasing, decreasing. And then our second derivative sign chart had a 2 and a 6 as critical values. And it was concave up, concave down, concave up. And so I said, well, look, after you get to 6, or after you get to 4, really, function is decreasing, but you can't be decreasing like this because you don't have any x-intercepts. And not only is it decreasing, but it's also concave up here, so you kind of have to flatten out. There's really no other choice but to have y equals 0 as a horizontal asymptote. And that was maybe a tiny fib. Technically, I suppose you could have y equals 1 as your horizontal asymptote, right? What's to say we couldn't have y equals 1? Nothing really, right? You could totally have said, well, maybe James is just a big liar. I'm not, but maybe I was. And maybe we had a horizontal asymptote that was like y equals some number larger than 0. Okay, well, L'Hopital's rule is what actually enables us to evaluate the horizontal, or find, I should say, the horizontal asymptote of this function. Actually, I guess I'm getting a tiny bit ahead of myself, but that's all right. I'm going to erase my graph because we don't really need it anymore. I want to find the horizontal asymptotes of this. So I want to find the limit as x goes to infinity of this particular expression. I should point out via the graph that we didn't have a horizontal asymptote to the left. If you looked at the limit as x went to negative infinity of x to the fourth e to the negative x, you would just get negative infinity to the fourth times e to the negative infinity. That's infinitely large. E to the positive infinity is also infinitely large. Infinitely large thing times an infinitely large thing is infinitely large. So as you go to the left, it goes up, which is what our graph is showing. But as you go to the right, we need more work. So I will say, just because it's already kind of showing up here, this is actually a different indeterminate form. So I want to really stress. I can't use Hopital's rule here. I don't even have a fraction. I don't even know I can use Hopital's rule. Do I have a 0 over 0 type? Maybe. Do I have an infinity over infinity type? I don't know. I have to do something so I can even think about using Hopital's rule. And before I get there, I should really say, what kind of indeterminate form is this? Well, x to the fourth, if x is going to infinity, this is going to infinity. And e to the negative x, where's e to the negative x going to if x is getting infinitely large? Good question, James. We could graph it. Here's e to the negative x. If x is going to infinity, what's e to the negative x getting closer and closer to? 0. This is I forget, someone asked me about this in the reflections, and there was a name for it that I didn't recognize, but this is another type of indeterminate form when you have an infinity times 0. Infinity times 0, you might think it's 0 because 0 times infinity could be 0. In fact, this one will end up being 0. But technically, when you hear anyone say the words indeterminate form, the thing you should think in your head is, oh, it can be anything. I could get 2. I could get pi. I could get 1,000,001, right? You can literally, by the way, side rant, I really hate that they redefine literally to also mean figuratively. It's one of the things that bothers me so much, right? It is actually true. They took the definition of literally and redefined it so people could. It is literally true that they define literally to mean literally or figuratively because of how it's used in speech. Kind of bothers me just a little bit, or a lot. Anyway, my wife was probably laughing in the other room like, my husband's insane. Okay, so anyway, indeterminate forms, which this is one of, infinity times 0, could have any possible value. In this case, we are going to get 0. But before we can get 0, we have to rewrite it in a form where we can use L'Hopital's rule, which means it has to be a fraction. Has to be a fraction, specifically a 0 over 0 or an infinity over infinity. We have two choices. One of them is good, one of them is not. One choice, the not good choice, would be to write this as the limit as x goes to infinity of e to the negative x over 1 over x to the fourth, or x to the negative fourth, whichever way you want to say it. Now, one thing I will say is you could try to use L'Hopital's rule here. This is a 0 over 0 form. E to the negative x is going to 0. 1 over x to the fourth, as x gets really large, is going to 0. But the problem with this is it doesn't really start to simplify. If you start taking the derivative of the top, which is going to be negative e to the negative x, and the derivative of the bottom, which is going to be negative 4x to the negative fifth. The derivative of the bottom, the powers of x are just going to get more and more negative the more we keep using Hopital's rule. The better way to go here, the only way to go here really, is to rewrite it the other way. Is to rewrite it as the limit as x goes to infinity of x to the fourth over, instead of saying 1 over e to the negative x, let's just call it e to the x. And now that's an infinity over infinity type. And I can definitely use Hopital's rule. So let's do it. So the derivative of the top is 4x cubed. The derivative of the bottom is e to the x. Still infinity over infinity. Let's do it again. So now it's the limit as x goes to infinity of the derivative of the top, which is 12x squared, over the derivative of the bottom, which is e to the x. Still infinity over infinity, but I think you guys can see what's going to happen. I'm going to keep taking the derivative of the top, which is a polynomial, and if you keep taking the derivative of a polynomial, it eventually is going to be a constant. Let's do it a couple more times. So derivative of 12x squared is 24x. The derivative of e to the x is again e to the x. And finally, using Hopital's rule one last time, you get the limit as x goes to infinity of the derivative of 24x is 24, and the derivative of e to the x is e to the x. Now I want to point out, we can't use Hopital's rule again. Even though it would give us the right answer, it's wrong to use it here because this is a non-infinity thing over infinity. Right? This is a number over infinity, but a number divided by something infinitely large is infinitesimally small. This is going to be 0. And what this example should really kind of point out to you is that e to the x is always bigger than the polynomial, right? No matter what power of x, right? We could have x to the 1000th power here and done Hopital's rule like 1,000 times to get down to some large constant over e to the x, and the limit of that would still be 0. So e to the x, or any exponential function, is always more powerful or grows more quickly than any polynomial, which is kind of neat, which you guys probably already knew that, but it's kind of nice to see it, right? This is actually real kind of visual proof that, oh yeah, no matter what power of x I have, if I've got x to a power over e to the x, that e to the x is always going to overpower it. Kind of interesting. All right, let's look at some other interesting examples. So most of the time, we're using Hopital's rule because we couldn't do anything else. A couple examples of that would be things like, I don't know, the limit as x goes to infinity of the natural log of x over x. Right? I don't know. I mean, I have a good idea, right? I've graphed both natural log of x and x, and they both do get infinitely large. I know that y equals x looks like this, and y equals natural log of x looks like this. So if you had to guess, which one do you think is the bigger one as x gets larger and larger and larger? Is y equals x the bigger one, or is y equals natural log of x the bigger one? I mean, it definitely looks like y equals x. Yeah. So it's good to think about your expectations when you're doing one of these limits. My expectation is that since x is the much bigger one and it's in the denominator, this is going to end up being 0. Let's find that. This is the limit as x goes to infinity. The derivative of the natural log of, I should use my L apostrophe H to let everybody know I'm using Hopital's rule. The derivative of the natural log of x is 1 over x. The derivative of x is 1. And then we get 1 over something infinitely large, which is, oh yeah, which is 0. I can't stress enough. Don't use the quotient rule, right? This is not a quotient rule. I know it's a fraction. We always have a fraction, but you're not taking the derivative of that. You're using Hopital's rule to take the limit. So please save yourself some pain and don't use the quotient rule if it's a limit. Let's look at another one. Let's look at the limit as x goes to infinity of the square root of x over the natural log of x. Square root looks like this. Sure. And at least the way I've drawn it, it's not super duper clear which one is getting bigger faster. I mean, they might be getting bigger at the same sort of rate. Let's find out. So when I'm thinking about limits, especially to infinity, and I've got something over something else, I'm usually thinking about comparing which one is growing faster. So if the limit ends up being 0, I know the bottom one grew faster. If the limit ends up being infinite, I know the top one grew faster. And if the limit ends up being actually a constant number, I erased that example. Like the example we did before where the limit ended up equaling 3/7, I know that the top is growing 3/7 the rate of the bottom. Yeah. So I might want to rewrite this as the limit as x goes to infinity of x to the 1/2 over the natural log of x. And I shouldn't get too carried away here. I should double check that I actually can use L'Hopital's rule. The top is going to infinity. The bottom is also going to infinity. But it's really important because sometimes someone's going to try and sneak one into you that you can't actually use L'Hopital's rule for. So it's really, really important to make sure you're always thinking, am I actually allowed to use L'Hopital's rule before I use L'Hopital's rule? So using L'Hopital's rule, the limit is x goes to infinity of the derivative of the top, which is 1/2 x to the minus 1/2, over the derivative of the bottom, which is 1 over x. And now I should probably simplify this a bit. I'm going to rewrite this as the limit as x goes to infinity of this top part is 1 over 2 root x. This bottom part is still 1 over x. And here's where it's easy to make the wrong choice. I could use L'Hopital's rule again. The top, definitely go into 0. The bottom, definitely go into 0. This is a 0 over 0. We could use L'Hopital's rule. We should not use L'Hopital's rule. If you've got powers of x and powers of x, we should be able to simplify this expression. So I'm going to rewrite this as the limit as x goes to infinity of 1 over 2 root x times the reciprocal of 1 over x, which is x over 1. And then x divided by the square root of x, or x divided by x to the 1/2, is just the square root of x, or x to the 1/2. So I can rewrite this as the limit as x goes to infinity of the square root of x over 2, or if you prefer, x to the 1/2 over 2. Either way, that's going to infinity. Infinity divided by 2 is still infinity. So this square root of x grows much faster than the natural logarithm, or the natural logarithm goes much slower than the square root of x. And again, that's actually true for any root. So if I said like the 3rd root or the 4th root or the 5th root or the 6th root or the 1000th root of x, eventually any root of x is always going to outpace a logarithm. It's actually very similar to the reason why an exponential always outpaces the power of x. Yeah, actually, let me show you, because I think it's kind of neat, and it only takes a moment. And I could show you by drawing it, but I could also use the tools at hand and show you on Desmos, which I think might be more illustrative. So let me show you on Desmos real quick here. I think it's kind of cool. Graphs are neat. Graphing is not always fun, but graphs are neat. So here's what I'm saying. I'm saying that if you have y equal to e to the x, it's always going to outpace any power of x, like x squared, right? The red one is definitely bigger than the blue one. And that's true whether or not we pick x to the 3rd, to the 4th. Right now, the blue one looks like it's bigger, but if you zoom way out, now, of course, you can't really see it because, right, it looks kind of crazy. But if you zoom out, eventually, that e to the x is going to be bigger than the other function, right? This e to the x is going to outpace that eventually. But let's go back to x squared because it's kind of easier to see. Maybe x cubed, right? With x cubed, you can see that, oh yeah, look, the red one does eventually overtake it. It becomes the bigger one. Well, this corresponds to what I was just saying about the logarithmic being bigger than, or sorry, smaller than a root, because I'm just talking about the inverse functions, right? The inverse function of e to the x is natural log of x. They're flipping across the line y equals x. This red graph flipped across that purple line is this green graph. And the cube root of x is the inverse function of x to the 1/3. Oh, come on. I always forget that I don't need those braces there. Sorry. Okay. So you guys can kind of see that, oh yeah, because eventually this blue function is going to be bigger than this red function, this black function is eventually going to overtake that green function. And again, right, it's hard to see it, but you can kind of see like, oh yeah, look, if you go way out, maybe. Now, I mean, it takes a really long time. Let's just go home. It's easier to see if the powers are squared. Right, we can see here, oh yeah, look, this red function is way bigger than this blue function, just like this black function is way bigger than this green function. And that's because when you take inverse functions, they kind of change roles. Right here, the red one's getting bigger faster, the blue one's not getting big as fast. When we flip them over the line y equals x, now this red one flips to the green one. It was getting bigger faster, now it's getting bigger much slower. This blue one flips to the black one. It was the one that was slower, now it's the one that's faster. So that's kind of something I think about a lot when I'm thinking about these L'Hopital's rule questions, is how it's kind of telling us, oh, some functions grow much faster than others. And I probably don't need to say that right now, but it could. So I need a little more light in here. One thing that I like to think about, and this is kind of just, this is looking more ahead, but I'm going to say it anyway, is that, no, actually not. It's not super salient right now. So let's look at some other examples. Let's look at some interesting 0 over 0 types. Like, I don't know, let's look something like this. The limit x goes to 0 of 2 to the x minus 1 over 3 to the sine of x minus 1. That's a 0 over 0 type of limit. If x is 0, that's too much light, I think. Sorry, I was like, it's too dark in here for my brain, but it's too light in here for the camera. It's a little better. Okay. 2 to the 0 is 1, 1 minus 1 is 0. 3 to the sine of 0 is 0. 3 to the 0 is 1, 1 minus 1 is 0. So it is a 0 over 0 type. So we can use L'Hopital's rule. Oh. What's the derivative of 2 to the x? Good question, James. Well, we know the derivative of e to the x is e to the x. We know the derivative of 2 to the x is 2 to the x times something times the natural log of 2. And the derivative of 3 to the x would be 3 to the x times natural log of 3. The derivative of 3 to the stuff is going to be 3 to the stuff times natural log of 3 times the derivative of that stuff, which is cosine of x. Every time after I use L'Hopital's rule, I then check, can I plug in 0 and get an answer? If I plug in 0, I get 2 to the 0 times natural log of 2. Well, it's not 0 or infinity, so I'm kind of, either I'm going to get an answer or this isn't going to work. And if I plug in 0 here, I get 3 to the 0 times natural log of 3 times cosine of 0, which is 1 times natural log of 2 over 1 times natural log of 3 times 1. So there's our answer. Natural log of 2 divided by natural log of 3. Kind of interesting. So let's look at another example. Do I want to do that one? kind of want to do that. Yeah, sure. I'm kind of not referring here. Let's do the limit. X goes to 0 of sine x minus x over x cubed. And again, let's check to make sure we can. 0 minus 0 over 0. Yep, it's a 0 over 0. So let's use L'Hopital's rule. So let's see, the derivative of sine minus x is cosine of x minus 1 over the derivative of x cubed is 3x squared. The bottom is certainly 0. The top is also 0, right? Cosine of 0 is 1. 1 minus 1 is 0. And then I'm going to use L'Hopital's rule again, right? This is 0 over 0. This is 0 over 0. So now the derivative of cosine of x is negative sine of x. And the derivative of 1 is 0. And the derivative of 3x squared is 6x. Still is 0 over 0. Now I will point out, if you wanted to, at this point you could say, hey, I know the limit of sine x over x is 1, and this is negative 1/6 times sine x over x. So you could just say it's negative 1/6 times 1. Or you can use L'Hopital's rule one more time. One more time. So the derivative of negative sine x is negative cosine of x. The derivative of 6x is 6. And then we can plug in 0 and get negative cosine of 0, which is negative 1 over 6. So here's a case where 0 over 0 ended up having a value of negative 1/6. And I just want to re-stress, right? Indeterminate forms can take on any value. Negative 1/6, natural log of 2 over natural log of 3, right? All kinds of funky numbers. I had another example in mind, and now it is gone from my head. Oh, I know what it is. Or I should say, I know approximately what it is. Let's do the limit. The limit as x goes to 0 of, oh, sorry, my brain just stopped working for a minute. Actually, I want the limit as x goes to 1, I think, of the natural log of x minus x plus 1 over, x e to the x minus x. Yeah, that's a good one. I didn't see, I think I left myself enough room. So let's check and see what the story is here. So let's see, if I plug in 1, natural log of 1 is 0, 0 minus 1 plus 1 is 0. The bottom, 1 times e to the 1. Oops, I know I made a mistake here. Yeah, that's what I wanted. Sorry. So actually, I should point out, right? If someone gave you this, you shouldn't use L'Hopital's rule. Because what do you get when you do this? Well, I get the natural log of 1 minus 1 plus 1 over 1 times e to the 1 minus 1, which is not a 0 over 0 type. Right, this is 0 minus 1 plus 1 over e minus 1. That's 0 over e minus 1. That's 0. So don't get tricked, even if it's accidental. Right? Don't get tricked. Someone might write something like this and try to trick you into using, I mean, not that your teachers are trying to trick you, but they're just trying to make sure that you understand when you can use L'Hopital's rule. This would be a good example of a problem where, like, it looks like it's probably 0 over 0. That looks complicated. I'm probably going to have to use L'Hopital's rule. Oh, no, we don't, because we don't actually have 0 over 0. So the problem I actually wanted to ask, which I was creating in my head as we were doing it, is this one. It's the same question, except it's going to be the limit as x approaches 1 of the natural log of x minus x plus 1 over x e to the x minus x. That's what I actually want. Smart. I know, real good, right? You're like, James, that's the same problem. X e to the x minus e to the x. That's what I actually wanted. And I feel like there's something I'm forgetting here. something silly that I want to make sure comes out right later. Let me just check one thing in my head. Darn it. Fine, we'll just do a one-step problem. I want this to be a two-step problem. I feel like there's something else I can do here to make this come out the way I want it to. Sure, we can do this. We can make it real exciting. That's probably not going to make it more exciting. Fine, I don't care. So now it's a 0 over 0 type. I was trying to make it so it had two steps, but I think it's just going to be one step. So it's going to be, let's use L'Hopital's rule. And we're going to get the limit as x goes to 1. Derivative of the top is 1 over x minus 1 plus 0. The derivative of the bottom, so the derivative of x e to the x, we have to use the product rule for. It's going to be 1 times e to the x plus x times e to the x minus e to the x. The derivative of e to the x is e to the x. So let's see what we've got. I'm going to simplify. I've got 1 over x minus 1 over e to the x plus x e to the x minus e to the x. So the e to the x cancel out. And now if I plug in 1, I get 1 minus 1, which is 0 over 1 times e to the 1. So I still get 0. But this is a different problem. Kind of interesting. It would be more interesting if I could actually remember the problem I was trying to think of, but it doesn't seem to be coming to me. Yeah. Oh, I know. Okay, yeah. All right. Yeah, we should do a couple more. So there are lots of types of L'Hopital's rules problem. So let's talk about other types of indeterminate forms. So there definitely are 0 over 0, infinity over infinity. But then there's like 4 other, at least, types of indeterminate forms. Here are the way we typically write them. So other indeterminate forms where after you do some manipulation, you will need to use L'Hopital's rule. But you have to do some manipulation to make it look like a fraction first. So 0 times infinity. It's definitely an indeterminate form. Infinity minus infinity, or negative infinity plus infinity, right? Same thing, really. It's also an indeterminate form. And then we have like the exponential forms, which are 1 to the infinity. It's an important one. It's not 1. So again, when I'm writing 1 to the infinity, what I'm really meaning is a number that's close to 1 to a power that's getting very large. And when I write 0 times infinity, the form I'm actually trying to capture with that is a very small number times a very large number. And infinity minus infinity is a very large number minus a very large number. So right, 1, if it was literally the number 1 raised to any power, it would be 1. But if it's a number that's close to 1 raised to a very large power, it can actually get really, really large. So we have 1 to the infinity. We also have 0 to the 0. Or infinity to the 0. These are all indeterminate forms that can take on any value. This one specifically is almost always 1, although there are some examples where it's not. This one can be lots of things. This one can be lots of things. So we'll talk about all these. Let's start with the 0 times infinity, which I know I already did an example of once. The 0 times infinity ones are typically the easiest to manipulate into what we want them to be. Where'd you go? Okay. Let's look at a few examples here. Let's look at the limit as x approaches 0 from the right of x times the natural log of x. So first off, is this an indeterminate form? Well, if x is going to 0, then x is going to 0. And what's natural log of x doing is x is approaching 0 from the right. Where are we getting to? It might be good to draw the natural log function.
Is it negative infinity?
It definitely is negative infinity. Thank you. Yeah.
Cool.
As we close in on 0 from the right, the logarithmic function goes down to negative infinity. That's an important one to remember because it often gets forgotten. So I want to rewrite this in a fractional way. And you almost, when you have a 0 times infinity, you almost always have a choice. You're going to bring one of the things down to the denominator as its reciprocal. So you could either write this as the limit as x goes to 0 from the right of x over the reciprocal of natural log of x, or you could write it as natural log of x over the reciprocal of x. And it's always going to be one type of either infinity or 0 over 0. If you bring the infinity thing down to the bottom as its reciprocal, well, then the bottom is a 1 over infinity, which is going to 0. So this is a 0 over 0 type. Whereas if you bring the 0 thing to the denominator as its reciprocal, the reciprocal of a 0 thing is an infinitely large thing, and this ends up being an infinity over infinity type. Which is why it works, right? If you've got a 0 times an infinity, doesn't matter if it's a plus or a minus infinity, a 0 times any sort of infinity, if you bring the infinity to the bottom as its reciprocal, you've got a 0 over 0. If you bring the 0 to the bottom as its reciprocal, you've got an infinity over infinity. And either of those lend themselves to be Hopital's rule. Either of those lend themselves to using Hopital's rule. So the question is, which one should we use? Well, there's usually a pretty obvious answer in that it's whichever one's derivative is going to suck less to take. That's going to suck, right? I don't want to take the derivative of 1 over natural log of x, or natural log of x to the negative 1 power. I have to use either the chain rule like this and get negative 1 times natural log of x to the negative 2 all times 1 over x. That seems terrible. Or use the quotient rule. Bottom derivative of the top minus top derivative of the bottom, all the bottom. So right, you would have to use the quotient rule if you wrote it like this for the derivative of the bottom. Typically, if you've got a logarithm, it usually stays on top. We're going to do it like this. It's much better. I'm going to write 1 over x to the negative 1. But it will tell you that you're going to be taking the derivative of 1 over x a lot for a lot of these problems. It's probably worth memorizing, if you haven't already, that the derivative of 1 over x is negative 1 over x squared. But we can write this as the limit as x goes to 0 from the right of natural log of x over x to the minus 1. And then use Hopital's rule. Hopital it up. The limit as x goes to 0 from the right, the derivative of the natural log of x is 1 over x. The derivative of x to the negative 1 is negative 1 times x to the negative 2. But I'd really rather write that as a fraction because it's just going to be easier to manipulate. So I'm going to re-express this as the limit as x goes to 0 from the right of 1 over x over negative 1 over x squared. Because then I can flip and multiply, and let's see what happens. You get the limit as x goes to 0 from the right of 1 over x times negative x, or x squared over negative 1 if you want. Which when I simplify that, that's just the limit as x goes to 0 from the right. X squared over x, you can cancel an x, you just get x over negative 1, which is negative x. And now we can plug in 0 and get 0. So this limit is 0. Which, if you were graphing x times natural log of x, would actually be super helpful. Because it would tell us that, in fact, I'm going to say more. So if I want to graph f of x equal to x times natural log of x, I'm going to find the usual things. I'm going to find, well, there isn't any y-intercept because the domain of this function is x greater than 0, or 0 to infinity if you like. We can't plug in 0. That's why we were taking the limit as x approaches 0 from the right, because the function is not defined for the left side of 0. X-intercept, we are going to have an x-intercept. if we set x natural log of x equal to 1, sorry, equal to 0, we get x equal to 1 because natural log of 1 is equal to 0. There is no vertical asymptote. You might think there was one, but we just did the work to show that there isn't, right? There could have potentially been a vertical asymptote at 0, right? Because maybe, right, natural log of x on its own does have a vertical asymptote at 0, but it doesn't now that you've multiplied it by x, because as we go to 0, we're going to be getting closer and closer to 0. Horizontal asymptote, there's also none. We know this because if you take the limit to infinity, you get infinity times infinity, right? These are both going to be infinitely large. So there's no horizontal asymptote, right? There's no one number, things are getting closer to. Let's do the first derivative stuff. It's not going to be terrible. So let's take the first derivative. It's going to be 1 times natural log of x plus x times 1 over x. So let's write f prime. That's going to simplify to the natural log of x plus 1. Set that equal to 0, and we get the natural log of x equals -1. So e to the natural log of x equals e to the -1. So x equals e to the -1, which is 1 over e. That's my critical value for the first derivative. And plug it into my reduced number line, right? Because I don't have anything to the left of 0. There's 1 over e. Pick a number larger than 1 over e to plug into the derivative, like 1. Natural log of 1 is 0, plus 1 is 1, so you get a positive derivative. Pick a number smaller than 1 over e to plug into. That's a little trickier. We could pick 1 over e squared, or e to the -2. I suppose I should write it over here. So be smart about this and go, okay, I plugged in x equals 1. Now I'm plugging in x equals e to the -2. If I plug in e to the -2, the natural log of e to the -2 is -2. -2 plus 1 is negative. So I'm decreasing, increasing. I have a critical value, a minimum, a relative minimum, at x equal to 1 over e. And then we can do the second derivative stuff, which is even easier. The second derivative is just going to be 1 over x. So my second derivative is 1 over x. The only critical value would be 0. That's the end of my domain. So pick a number larger than x, 1, sorry, larger than 0, not larger than x, 1, and plug it in, and oh, look, it's positive. That means it's concave up everywhere. Let's graph this thing. So before we had L'Hopital's rule, we'd be kind of stuck with what's going on as we got closer and closer to 0. But now we know that, well, let's graph the thing. So I have X-Intercept at 1, relative minimum at x equals 1 over e. So here's 1, there's an X-Intercept. 1 over e is like 0.3-ish. It's like right there. And I suppose I can find the y value. My function is x natural log of x. If I plug in 1 over e, I get 1 over e times the natural log of 1 over e. The natural log of 1 over e is -1, right? It's the natural log of e to the -1st, which is just -1. So it's -1 over e. So I plug in 1 over e, I get -1 over e. So that's my relative minimum right about there. At about 0.3, comma -0.3. And so that's a minimum. And before we might say, well, shoot, what happens over here? Like, how do I know it goes to 0? Maybe it does something like, maybe it just ends like right there at -1 over e squared for all I know. Well, we did the work. We found that as x approaches 0, the function also approaches 0. So it actually does have an open circle or kind of a hole at the origin, and it looks like that. Kind of neat. It's kind of a neat graph. Let's do some more L'Hopital's rule problems. I think it's going to be all L'Hopital's rule today because there's a lot to say about it. So for this problem here, it is an indeterminate form. Is it an indeterminate form? Now I'm looking at it like, Yeah, I think I've written something. Oh yeah, that's because I've written the wrong thing. That's fine. Let me fix it here and just double check. I know I've written the wrong thing, but I should check. So if this problem was written as is, it's actually not, right? You've got a 0 times the sine of infinity. How would you do this problem? That's a good question. This problem is a squeeze theorem problem, right? I've got sine of something that I don't really know what that something is. It's something that's kind of growing infinitely large. So what I would say here, and it's been a while since we talked about the squeeze theorem, I would say, oh yeah, sine of 4 over x cubed is between 1 and -1. And then I would multiply everything by x cubed. So if negative x cubed is less than or equal to x cubed times sine of 4 over x cubed is less than or equal to x cubed. The limit of this, as x goes to 0, this goes to 0, this goes to 0. So by the squeeze theorem, the middle thing has to go to 0. I know that's kind of like an abbreviated, right? Like you would write more words and stuff if you were actually doing this problem, but that's how you would do this problem if it was a 0. But I didn't actually mean for it to be a 0. I meant for it to be an infinity. So I should point out though that right over here we're saying, oh yeah, the limit as x goes to 0 of x cubed sine of 4 over x cubed is indeed 0. This, on the other hand, is going to be different. So now I've got an infinity times a 0 form. X cubed is going to infinity. Sine of 4 over x cubed is going to sine of 0, which is 0. All right. So let's see what we get. Well, I should say let's see what we get by rewriting this so we can use Hopital's rule. Right? If we've got an infinity times a 0, we want to rewrite it. And typically the way you decide what to put on the bottom is whatever is less complicated. The only kind of exception is if you've got an x to a power of times an e to the x, you always want to bring the e to the x thing to the bottom. For this one, I'm going to rewrite this as the limit as x goes to infinity of sine of 4 over x cubed over 1 over x cubed, which is a 0 over 0 form. And now we can use Hopital's rule. Okay. So the derivative of 1 over x cubed is the derivative of x to the negative third. The derivative of x to the negative third is negative 3x to the negative fourth, or negative 3 over x to the fourth. And I am writing it like that kind of on purpose. But I mean, you could, not really actually, I'm kind of lying to myself here. This is, right, the derivative is negative 3x to the negative fourth. And here, the derivative of sine of the stuff is cosine of the stuff. And then the derivative of 4 over x cubed, well, that's 4 times x to the negative third. The derivative there is going to be 4 times negative 3x to the negative fourth. And look what happens. These things cancel out. Those are exactly the same. This happens a lot, actually, where you've got like function of a thing over very similar thing. And on top, when you take the derivative using the chain rule, the derivative of the inside essentially matches up with the derivative of the bottom part there. And so they pretty much cancel out. That happens a lot. So those cancel out. And now look what we're left with. We're left with 4 times cosine of a thing. And that thing is going to 0. And cosine of 0 is 1. So this is 1 times 4. So here was an infinity times 0 indeterminate form that ended up having a value of 4. Interesting. You might also recognize, in case you're wondering, this is kind of a sine of 0 over 0 kind of problem. It's just, right, you could even, if you wanted to, you could multiply this by a 4 over 4. And then you'd be like, oh, sine of 0 over 0, where the zeros are the same, that goes to 1, and then 4 times 1 is 4. You can also see it that way, although I think Hopital's rule is in order here. Let's look at some infinity minus infinity forms. This is infinity minus infinity, right? The bottom natural log of 1 is 0. 1 over 0 blows up to infinity. And this is This is a 1 over a small positive number because we're approaching 1 from the right. Similarly here, 1 minus 1 is a small 0-ish number, but it's a slightly positive because we're approaching 1 from the right. So we've got a positive infinity minus a positive infinity. It is important to check the signs of your infinities, because if you have just like infinity minus negative infinity, that's not indeterminate. That just blows up to infinity because you got infinity plus infinity. That's not what we're doing though. So yikes, how do we write that as one fraction? Well, how do we usually combine two fractions into one fraction if we're adding or subtracting? Common denominator. So I'm going to multiply this by x minus 1 over x minus 1, and this by natural log of x over natural log of x. So I'll rewrite this as the limit as x goes to 1 from the right of x minus 1 minus natural log of x over x minus 1 times the natural log of x. And then pretty much guaranteed to have an indeterminate form of the right type. Right? This should be automatically a 0 over 0 or an infinity over infinity. I should check, but it should work. Let's check. If I plug in 1, oh, yeah, that's right, yeah. 1 minus 1 is 0, minus natural log of 1 is 0. Check. 1 minus 1 is 0 times natural log of 1 is also 0, 0 times 0 is 0. Check. So let's use L'Hopital's rule. So if the limit as x approaches 1 from the right, derivative of the top is 1 minus 0 minus 1 over x. Derivative of the bottom, I have to use the product rule. So it's derivative of x minus 1 times the natural log of x minus x minus 1. Sorry, minus, where am I getting minus from? What kind of crazy person am I? Derivative of the first thing times the second thing plus x minus 1 times the derivative of the natural log of x, which is 1 over x. And if I plug in 1, I get 1 minus 0 minus 1, which is 0. On the bottom, I get natural log of 1, which is 0, plus 0 times 1, which is also 0. So I still have a 0 over 0, so I probably need to use L'Hopital's rule again. Before I use L'Hopital's rule again, I should simplify. Limit as x goes to 1 of 1 minus 1 over x over natural log of x. And if I distribute the 1 over x here, I get 1 over x times x, which is 1, minus 1 over x. Okay, let's take the derivative. Sorry, let's use L'Hopital's rule to see if we can get something that works. Using L'Hopital's rule, limit as x goes to 1, derivative of the top is 0 minus, the derivative of 1 over x is negative 1 over x squared. It's going to come up a lot. I suggest you memorize it. The derivative of the bottom is 1 over x plus 1 over x squared. Whew. And if x was approaching 0, I'd be in trouble, or at least I'd have to do more work, but it's not. It's approaching 1. Right? It's easy to think here, oh, look, I've got like an indeterminate form. No, we don't. This is not indeterminate. This is definitely 0 plus 1 over 1 plus 1, which is 1/2. It's kind of interesting. So here, infinity minus infinity is 1/2. This infinity is 1/2 bigger than that infinity. Kind of funny when you say it that way. Anyway. Let's look at another infinity minus infinity. Or actually, I think we're going to write it. Yeah. Infinity minus infinity ones, I think, are some of the trickier ones. Especially this next one I'm about to throw at you. Let's do the limit as x approaches negative infinity. Oh, interesting. Of the square root of x squared plus, what number do I want to pick here? Let's go with 16x just to be on the safe side. Minus x plus x. This is an infinity minus infinity type. How do we know? Well, let's actually write down something just to make sure that that is actually true. So how do I know that this is going to infinity? I don't actually yet. I've got negative infinity squared, which is going to positive infinity. Then I've got plus 16 times x, which is going to minus infinity. So I've got positive infinity. Oh, shoot, that's an indeterminate form. Infinity minus infinity. So here's the thing. When it's specifically powers of x, we know that bigger powers overpower smaller powers. So this x squared is going to overpower the 16x. this positive infinity is going to be way more positive than this negative infinity. But there is an easier way you can see it. You can say that x squared plus 16x is x times x plus 16. And then if x is going to minus infinity, you get a minus infinity times a minus infinity, which is positive infinity. So this starts going to infinity plus a negative infinity. So yeah, we do have an infinity plus a negative infinity, which is an indeterminate form. Now you might ask, hey James, you just said the bigger power overpowers the smaller power. Why doesn't this overpower that? Because this isn't a bigger power. Yeah, there's an x squared in there, but there's a square root of x squared. So this piece here, although it's not exactly like it, it does act like x, which is kind of interesting. In fact, I think if you graph, I'm not sure about this, but I'm pretty sure if you graph like just y equals the square root of x squared plus 16x, I think it'll have like a slant asymptote at y equals x. Not positive, I need to check on that, but something like that is true, if not exactly that. Anyway, I've got an infinity minus infinity. What the heck do I do? The only thing we really usually do when you have a square root plus or minus something else is we multiply by the conjugate. So I'm going to write this as the limit x goes to minus infinity of the square root of x squared plus 16x plus x over 1, just to make it easier, times the conjugate over itself, which is the square root of x squared plus 16x minus x over the same darn thing. Which is not indeterminate, right? This is infinity minus minus infinity, which is infinity plus infinity. So, okay. It's okay to multiply by infinity, no problem. Okay, why do you multiply the conjugate? To get rid of the square roots. This times this, you get the first thing squared minus the second thing squared. So you're going to get the limit as x goes to minus infinity of x squared plus 16x minus x squared all over this. Okay, we can cancel the x squareds. Okay, so let me tell you guys, this is kind of interesting. I limited x goes to minus infinity. This is kind of like a rational function, where the degree on top and the degree on the bottom are kind of the same. Kind of, right? It's not really a rational function, because the bottom's not a polynomial. But the degree on top is 1, and the degree on the bottom is essentially 1, because this is x to the first, and the square root of x squared is kind of like x to the first. So what I'm trying to say here is that, I mean, I guess if you wanted to, we could use L'Hopital's rule. Ooh, if you wanted to, we could try to use L'Hopital's rule here. Right. Technically, do I want to use L'Hopital's rule here? I don't remember now. Do I want to use L'Hopital's rule? I'm pretty sure I don't. I'm pretty sure using L'Hopital's rule here is terrible. Yeah. I can show you why it's terrible. I don't really want to, but I could. I will. So if you try to use L'Hopital's rule here, you get stuck in an infinite loop. I think. No, I'm not. I'm like, probably. Maybe. Let's try using L'Hopital's rule and see what happens. First of all, do I have an infinity over infinity type? I do. The top is going to negative infinity. The bottom is going to positive infinity. So let's see what happens here. I think this is not going to work, but it could work. We use L'Hopital's rule with the limit. X goes to minus infinity. I really don't want to use L'Hopital's rule. It looks like not a lot of fun. I get 16 on top. On the bottom, so the derivative of the square root of x squared plus 16x is 1/2 times x squared plus 16x to the negative 1/2 times 2x plus 16 minus 1. That looks heinous. I'm going to rewrite it. Something to the negative 1/2 means you're dividing by its square root. So I'm going to rewrite this as 1/2 times 2x plus 16 over the square root of this. And now I want to tell you that this is still terrible. You still got something going to some sort of infinity on top and something going to some sort of infinity on the bottom. And when you have something like this, you end up getting stuck in a loop where you keep just doing this over and over and over. Basically, if you simplify this, you end up with the square root part on the top and the 2x part on the bottom. And if you do it again, it just flips back and forth. So don't get stuck here. You might see someone ask this question in a different way. You might see someone ask something like I've definitely seen this question before, where people ask you to do like the limit as x goes to infinity or something a little bit simpler looking. Like, I got a weird like piece of grossness on my pen. Come on, pen, work. Just destroy the pen. There we go. It's working now. Yeah. There's a great limit that does not work if you use L'Hopital's rule. Let me just show you. It's infinity over infinity. If you try and use L'Hopital's rule, the derivative of the top is 1. The derivative of the bottom is 1/2 x squared plus 1 to the negative 1/2 times 2x. The 2's cancel. This is 1 over x over the square root of x squared plus 1, which is the limit as x goes to infinity of the square root of x squared plus 1 over x. You're stuck. This keeps just flipping back and forth, back and forth, back and forth. How do you deal with this? The same way we're going to deal with the one we're doing. So we actually don't use L'Hopital's rule here. Sometimes L'Hopital's rule is a trap. It's a trap. Okay, sorry. So what do we do instead? We treat this like we would have treated something like 3x squared plus 5x plus 1 over 7x squared plus 6x minus 2. But we actually do the thing where we factor out the biggest power, divide by this biggest power top to bottom. So I'm going to divide both the top and bottom by x, or factor out an x from the top to the bottom. Before I can do that, though, I have to deal with this. And this is where the extra part comes in. So limit as x goes to minus infinity. 16x on top. To factor out an x from here, I have to factor out an x squared from inside the square root. So I'm going to factor out a square root. I'm going to have an x squared times 1 plus 16 over x minus x. All right, here comes the trick question. What's the square root of x squared? Like if we're just quiet long enough, he'll say it. Which is true. I will say it eventually. Okay, so the square root of x squared is the absolute value of x. And in this particular problem, since x is negative, the absolute value of x is negative x, because you need a negative x to turn the already negative value into a positive value. So this square root of x squared becomes negative x square root of 1 plus 16 over x minus x. And now I'm really worried. No, I'm not worried. I'm not worried. Okay. Anyone want more clarification on that? It's usually kind of a sticky point. All right, now I'm going to factor an x out from the bottom. So I'm left with the limit as x goes to minus infinity of 16x over minus x times the square root of 1 plus 16 over x minus 1. Sorry, I factored out a minus x accidentally, so I guess there should be a plus 1 there. And then this x here can cancel with the x there. And then I can just take the limit. The top is 16. The bottom is going to the square root of 1 plus 0, which is 1, plus 1. So the answer is 8. So sometimes L'Hopital's rule isn't the way to go for an indeterminate form. Sometimes it can be a trap. Just too bad. Another example of a trap This is less of a trap, but it's still a trap. So this is definitely a trap, right? You have to do the thing we did here. So for this problem, if you wanted to figure this one out, instead of using Hopital's rule, just like the previous problem, you have to factor out x squared from the denominator. Sorry, from inside the square root. So you write this as the square root of x squared times 1 plus 1 over x squared. And then the square root of x squared is again the absolute value of x. In this case, since x is going to positive infinity, the absolute value of x is just x. And so these cancel, and you get 1 over 1 plus 0, or 1 over the square root of 1 plus 0, which is 1 over 1, just 1. It's kind of interesting, though. If you graph this, the limit to the right is positive 1, so you have a horizontal asymptote of y equals 1 to the right. But the limit to the left, as you go to negative infinity, you'd have a negative there, and so it would be negative 1. So this is an example of a function that has two different horizontal asymptotes. The function x over x squared of x squared plus 1 looks like this. It's kind of neat. It kind of looks like inverse tangent. Anyway, so let's talk about some of the other indeterminate forms. Some of the, what I usually refer to as the exponential indeterminate forms, because they do come up a bit. In fact, let's start off with kind of a classic example. The limit we already know. Yeah, not you. Let's do this one. Let's do the limit as x goes to infinity of 1 plus 1 over x to the x. This is the definition of E. Hopefully you guys have seen this before. Right, we know, so we're going to show that this is equal to E, but this is a limit we should know already. I feel like weird dust in my fingernails. It's terrible. There's two different ways of dealing with this. Some people, and either way is good. Some people prefer to do this. We're going to look at the limit as x goes to infinity of e to the natural log of 1 plus 1 over x to the x. That is one way to handle it. Another way to deal with it is to instead say, I'm going to look at the limit of just the natural log of this and then say that my result is e to that answer. And that's probably the easier way to write it. So let me do it that way. So if I want to find the limit as x goes to infinity of 1 plus 1 over x to the x, we're going to examine the limit as x goes to infinity of the natural log of 1 plus 1 over x to the x. Okay, so watch what happens. We're going to bring down the x. That's the reason we took the natural log, is because that thing in the exponent is problematic. So the limit as x goes to infinity of x times the natural log of 1 plus 1 over x. And now we've got an infinity times a 0. 1 over x goes to 0. 1 plus 0 is 1. Natural log of 1 is 0. We're going to bring down the x to the denominator. This is going to be the limit as x goes to infinity of the natural log of 1 plus 1 over x over 1 over x. All right. Now we've got a 0 over 0 form. Let's use Hopital's rule. I was going to do it. Okay, well, I'll come back. I had another one I wanted to tell you that we should use Hopital's rule. So this is the one where we're really going to do the derivative of 1 over x plus. So the derivative of 1 over x is negative 1 over x squared. So the derivative of the bottom is negative 1 over x squared. The derivative of the natural log of this is 1 over the stuff times the derivative of the stuff. But the derivative of 1 plus 1 over x is 0 plus the derivative of 1 over x, which is negative 1 over x squared. So those cancel out right off the bat, which is nice. We like that. And then the rest of it we can just find. 1 over x is going to 0. 1 over 1 plus 0 is 1. Now we have to be careful. The answer is not 1. We found the limit of the natural log. So what we're doing is we're saying, hey, look, this is equal to the limit as x goes to infinity of e to the natural log of 1 plus 1 over x to the x. And then the thing about a limit is the limit of e to a thing is equal to e to the limit of that thing. We just found that, right? That's all the work we just did here. That's 1. So the limit of that expression is in fact e, which is cool. And a lot of these answers are going to either be e or have e because they're all going to involve doing this thing where we say, I'm going to take the limit instead of the thing, it's going to be e to the natural log of that thing. Let's do a number of examples. Let's do this one. No, let's not do that one. That one's kind of crazy. I mean, we can, sure. Why not? Let's look at the limit as x goes to infinity of x to the 1 over natural log of x, which is an infinity to the 0th form. Right? I don't know. It's infinity to the 0. And again, we're going to think of this as the limit as x goes to infinity of e to the natural log of x to the 1 over x. Sorry, x to the 1 over natural log of x. Apologies. The e to the natural log of this, which is kind of funky looking. Which is then, we can even just, this one actually lends itself to working out really nicely. So normally I would just look at this on its own, but here we're just going to work it out. Check this out. The limit as x goes to infinity. So e to the natural log of x to the power, this power can come down in front. But look at what that's going to be. That's going to be e to the 1 over natural log of x times the natural log of x. Which is weirdly the limit as x goes to infinity of e, which is e. So this one's just e, right? I don't have to go back and make it e to the e because, right, I didn't actually do the thing I did in the previous problem. So it's kind of weird. And if you graph this, it's really kind of interesting. If you graph on a graphing calculator or Desmos x to the 1 over natural log of x, it's just equal to e whenever x is positive. It's kind of bizarre, right? We did e to the natural log of the thing, which is still the same, and we got the e to the natural log of my thing ended up just being e, which means the original thing is e, but the domain is where x is positive. Kind of weird. It's really weird, actually. So it kind of trips me up sometimes. But let's look at some more typical examples, like this one. Sure. So typically with these exponential forms, it's usually going to be some sort of Hopital's rule deal where you're going to have to do a natural log kind of thing. So let's look at the limit as x goes to 0 from the right of sine of x to the 1 over x, which is a 0 to the infinitieth power, which I don't know if that's actually an indeterminate form. We can still work it like it is though. But yeah, I feel like this isn't indeterminate, right? Let's think about it this way. We're still going to do it, but I want to kind of give you guys some right? Think about what's happening here, right? If this is 0, or at least close to 0, it's very, very small. It's definitely less than 1. If you have a very small number raised to the infinity power, when you multiply it by itself, it seems like it should be getting smaller and smaller and smaller and smaller and smaller. And we might not even need L'Hopital's rule to evaluate this. But let's try and work it, because I don't really know. So I'm going to write this as the limit as x goes to 0 of e to the natural log of sine of x to the 1 over x. And I'm really going to think of that as, I'm going to write like this. So I'm going to let the limit pass through the exponential function into the exponent. I'm going to write it as e to the limit as x goes to 0 from the right of this, which I'm going to bring down to 1 over x. It'll be 1 over x times the natural log of sine of x. And actually, yeah, this is not a L'Hopital's rule problem. It's still a problem where we need to use this process, but I'm going to rewrite it just to make it a little more clear. This is e to the limit as x goes to 0 from the right of natural log of sine of x over x. I'm not going to write it as over 1 over x. Sorry, over 1 over 1 over x. That would be silly. I've already got the x in the denominator. Okay, let me ask you guys. Where's the bottom going to? Easy answer. 0. Harder question. Well, slightly harder question. We know sine is going to 0 as well. Where's the natural log of 0 going to? I know someone said it before. It's going to negative infinity. So this here is not an indeterminate form. Negative infinity over 0 is not indeterminate. That's definitely negative infinity, right? You've got something that's really, really negatively large over something that's really, really positively small. Really, really negative large number divided by really, really positive small, really, really small positive number is a really, really large negative number. So this thing is going to negative infinity. So this is going to equal e to the negative infinity, which is going to go to 0. So that's our answer here. L'Hopital's rule, not only not required, not allowed. I will say you probably could have reasonably stated that since you've got a number that is close to 0 and you're multiplying it by itself an infinite number of times, it is getting smaller and smaller and smaller, right? It can't get larger. That's not entirely true for other things. So, for example, what if I had the limit as x goes to 0 from the right of 1 minus 2x to the 1 over x? So I've seen people incorrectly try to argue that this limit is 0 as well. Because they've said, well, I've got a number that's slightly less than 1. And I'm multiplying it by itself an infinite number of times. And if it's slightly less than 1, that means that it's going to make itself smaller and smaller and smaller and smaller every time. And while I can kind of get behind that reasoning, the problem here is that while this number is less than 1, it's getting very, very close to 1. And so even though you're multiplying by things that are technically a tiny bit less than 1, the amount that you're making it smaller by is so insignificant that you can't make that argument. Whereas for the previous problem, it's okay to say, well, this is 0, and 0 times itself a bunch of times, or something close to 0, is still going to be very, very small. The argument does not hold up here. We have to use L'Hopital's rule at some point for this one, for sure. And this is a 0, not a 0, a 1 to the infinity form. And I will mention, because it's true, a 1 to the infinity almost always ends up being e to the something. I mean, Most of these always end up being e to the something. It's just sometimes e to the something is e to the 0, which is 1, which is not particularly exciting. But let's do this one. Let's see. So I'm going to write this as the limit as x goes to 0 from the right of e to the natural log of 1 minus 2x to the 1 over x. I'm going to let the limit come up into the exponent, and I'm also going to bring the 1 over x down. So I'm going to write this as e to the 1 over x times the natural log of 1 minus 2x. But I'm also going to write the limit up there as x goes to 0. I know it's kind of a lot. So then we're going to write this as e to the limit as x goes to 0 from the right of natural log of 1 minus 2x over x. So when you're bringing this 1 over x down to the bottom, don't make it harder than it has to be. The x is already in the denominator. You could, but it'd feel real not smart to write this as 1 over x. I mean, it's not wrong, but it's not right. I mean, it's right, but it's not the way you want to do it. So in this case, we're going to use L'Hopital's rule because I've got a 0 over 0, right? Natural log of 1 over 0 is 0 over 0. I'm going to get e to the limit as x goes to 0 from the right. Derivative of the bottom is 1. The derivative of the top is 1 over my stuff times the derivative of my stuff, which is negative 2. I usually put the brackets around the limit. Not that it really matters, but it kind of matters. Okay, now as x goes to 0, I get 1 over 1 times negative 2 over 1, which is negative 2. So the answer here is e to the negative 2. So 1 minus 2x to the 1 over x goes to e to the negative second, or 1 over e squared, as x goes to 0. Let's see, we probably got time for one more. Oh yeah, let me talk about a couple things. So I will say generally, right, for exponential forms, you're always going to do this thing where you do the e to the natural log. If you prefer, you can just say, and some people really do prefer not to write it this way, but you could say, I'm going to look at the limit as x goes to 0 from the right of just the natural log of 1 minus 2x to the 1 over x. And then I'm going to say this limit, this is going to equal e to the whatever I get right there. Some people prefer to do it that way, where they take the natural log of the thing they're trying to take the limit of, find whatever that's equal to, and then say that your actual answer is e to the that. If we had done that here, right, if we had ignored the e part and said, I'm going to do the limit of the natural log, we would have just gotten the negative 2, and then our answer would have been e to the negative 2. It's just a different way of writing it. But let me talk about two problems, one where you can't use L'Hopital's rule and one where you shouldn't. Well, I will say you can, but it won't help. So here's one problem. The limit as x goes to infinity of e to the 3x plus e to the 2x over e to the 3x plus e to the x. If you use L'Hopital's rule here, you're just going to get stuck in an infinite loop. Using L'Hopital's, so it is infinity over infinity. Using L'Hopital's rule, you're going to get the derivative of e to the 3x is e to the 3x times 3. Derivative of e to the 2x is e to the 2x times 2 over the same kind of thing, 3 e to the 3x plus e to the x. And I think you guys can see that this is just going to keep happening, right? The next derivative, the next L'Hopital's rule is going to be 9 e to the 3x plus 4 e to the 2x over 9 e to the 3x plus e to the x. And it's just going to keep going and going and going. It's always going to be infinity over infinity. It's never going to get to something that's not indeterminate. This is actually very similar to the problems where we have like just rational functions, like the x squared, like the 3x squared plus whatever over 7x squared plus whatever. And instead of using Hopital's rule, another way to go about that is to divide by the thing that's getting biggest fastest. If I wanted to do this limit, without using Hopital's rule, I would just divide the top and bottom by x squared. And get 3 plus things that are going to 0 over 7 plus things that are going to 0. I'm going to use the same idea there. I'm going to divide everything by the thing that's growing fastest, which is e to the highest power, e to the 3x. So I'm going to divide everything by e to the 3x. And look at what I get. I get the limit as x goes to infinity of 1 plus e to the 2x over e to the 3x is e to the negative x, or 1 over e to the x, over 1 plus, this is going to be 1 over e to the 2x. And 1 over e to the x is going to go to 0, and 1 over e to the 2x is going to go to 0, which is going to equal 1. So yeah, we want to divide by the thing that's getting biggest. I will point out that if you did the limit as x goes to negative infinity for this problem, so let me ask you guys, if x is going to negative infinity, well, all of these things are actually going to 0. Which one goes to 0 the slowest? E to the 3x, e to the 2x, or e to the x? It's an interesting question. The answer is e to the x, right? If e to the x grows the slowest, it also gets smallest the slowest. So here I would actually divide everything by e to the x. So I did everything by e to the x, I'm just going to do the work. I get e to the 2x plus e to the x over e to the 2x plus 1. I divided everything by e to the x. And now as x goes to negative infinity, this goes to 0, this goes to 0, this goes to 0, and you get 0 over 1, which is 0. Whereas this would be the indeterminate form 0 over 0. So that works too. Yeah, we got time. Okay, the last trap someone might try to set for you is the following. And again, I don't really think your teachers are trying to trap you. That's just a way of saying it. The last tricky kind of problem is this. Let's make it real terrible. This is a 0 over 0 type of limit. And you could use Hopital's rule. And if you did, you would have to do it 3 times. And as you might be aware, the derivative of the bottom 3 times is fine. The derivative of sine cubed, the first time is okay, the second time is pretty gross, and the third time is really terrible, right? If you try and do Hopital's rule, okay, the first time is not so bad. The derivative of 2x cubed is 6x squared. The derivative of some stuff to the third power is 3 times your stuff to the second power times the derivative of your stuff. But then I still have a 0 over 0, right? Sine of 0 is 0, cosine of 0 is 1, 0 times 1 is 0 over 0. So if I start using Hopital's rule again, this is where things get really awful. I have definitely asked questions like this on the test. And I've probably even told my students to not use Hopital's rule because I'm not usually a jerk. But you don't want to use Hopital's rule here because the second step is really, really gross. I have to use the product rule here. The derivative, I guess I can cancel a 3 and a 3 there to get a 2. So the derivative of the bottom is 4x. The derivative of the top, so using the product rule, the derivative of sine squared, the derivative of some stuff squared is 2 times my stuff times the derivative of my stuff times the other piece plus, now that part left alone, times the derivative of that. So now I'm having to, so this is right, this is 2 sine x cosine squared x plus, or minus, I guess, sine cubed x. And then to do the last step of Hopital's rule, which I'm not going to do, the bottom derivative would be 4. The top derivative is really disgusting, right? I have to use the product rule and the chain rule here and the chain rule there. It's just like, I don't want to do it. More importantly, we don't have to do it. We have a method for doing this. So if I've got sine cubed x over 2x cubed, I can write this as the limit as x goes to 0 of sine of x times sine of x times sine of x times something over 2x cubed. And what do I wish was beneath each of my sine of x's? X. Because the limit as x goes to 0, sine x over x, we know is 1. And then this x cubed cancels with this x cubed. These each have a limit of 1. So my answer is 1 times 1 times 1 times 1/2. And this is how you should do that problem. Right? Look how much less work it was already. I haven't even finished this problem, and already this is way less work. So if someone gives you a problem like this where you've got a power of sine, really any power of sine other than 1, sine squared is not too terrible, but anything higher than squared is definitely insane. Don't use L'Hopital's rule. Use other methods. So sometimes L'Hopital's rule is a great tool when we use it appropriately, but if you use it for the wrong thing, well, first of all, we only can use it when it's 0 over 0 or infinity over infinity. Right? Any other form, you have to make it look like a 0 over 0 or infinity over infinity. And moreover, there are some specific types of problems like this where if you use it, it's going to suck. Or like this where you can't even really use it because you get caught in the loop. So just be cautious with your use of L'Hopital's rule. It's great when it works. It's really, really maddening when it doesn't.